you very much. Yeah, I think it might seem a little strange to have a non-expert in climate change talk about climate change, but it's not really the process of climate change that this talk is about. It's about solutions, and I started getting interested in this topic about 15 years ago. I started to think about my carbon footprint and whatnot, and really about 7 to 10 years ago, I really started to get freaked out about how clear the science was, but also how badly I personally was doing in terms of my carbon footprint, probably in the top 1 or 2% worldwide at the time because of my flying for work. I was an assistant professor and trying to get my research and my students' research in front of as many people as possible, flying around the world. And is very, very carbon intensive. And so I started to look to solutions. And so I've been interested in this for a long time and now trying to work on this for a long time. So here we go. There we go. Okay, so this is not a climate science talk necessarily, but it's good to cover the basics. This is basically an energy balance problem. There's a lot going on in this figure, I apologize, but it's basically fairly simple. The incoming sunlight, mostly in the form of visible light, there's about 342 watts per square meter. That is, this is an energy balance problem, and the only way energy can come in or out, of course, is through radiation, because we're surrounded by vacuum. So yeah, the incoming radiation is from the sun, and there's 342 watts per square meter. That's averaged over the day and night side. And 30% of it is immediately reflected by the atmosphere and by the surface, but 70% gets through and is absorbed, some heating the atmosphere, but mostly heating the surface of the Earth. Now, as if we didn't radiate that heat outward, we would warm up, and we would continue to warm up until we would start emitting thermally. Our thermal black body radiation scales as temperature to the 4th power, and eventually we would get to a temperature high enough where we would our emitted infrared radiation, thermal radiation, would offset the incoming sunlight. And I make all my students do this calculation. It's not very difficult. And actually what you come to, if you don't have greenhouse gases in your atmosphere, is that the equilibrium temperature that the Earth would come to, if we had this, 30% of incident radiation reflected, is 0 degrees Fahrenheit. So it's extremely cold, and the entire Earth would be a ball of ice. And the only reason that we are here at all and alive is because of greenhouse gases. So greenhouse gases make the Earth not a black body, and it absorbs some of the infrared light that is trying to escape from the surface, slowing the process. And ultimately, the Earth needs to come to a larger temperature with additional black body radiation, thermal radiation, to overcome those greenhouse gases. And now it's in, or it has been in equilibrium for in the short term, thousands of years, and there's about 235 watts per square meter coming out, which is the same as that is actually absorbed here. And so these greenhouse gases have been here a long time, and the primary greenhouse gas is carbon dioxide. And I'm showing you here the concentration in parts per million on the y-axis here for the last 10,000 years. I like to show this plot because it's kind of incredibly strange in the history of the Earth that we have this remarkably constant level of greenhouse gases in the atmosphere, where we went from about 260 to 280 parts per million over 10,000 years. And it's exactly this time period when modern civilization came about, when this stable period in the greenhouse gases, this stable period in temperature, is when agriculture began, when humans came out of the Stone Age and into the Bronze and Iron Age ages, and when modern civilization came about. And a couple hundred years ago, over to the right of the plot here, we found a whole bunch of energy in the form of fossil fuels, coal, gas, and oil underground. And we were no longer limited in what we did in society by our hands and our muscles and the food we eat, but instead could increase this by orders of magnitude by just burning these fossil fuels. And these fossil fuels are hydrocarbons, and when we burn them, they create carbon dioxide. And because of it, we have increased the concentration of carbon dioxide in the atmosphere from 270, 275 or so before the Industrial Revolution to about 415 today. I want to emphasize that that is not a small perturbation. That is a 50% increase in our greenhouse gas blanket, right? So this, if you put a 50% thicker blanket on yourself at night, you will expect the temperature underneath the blanket to warm, and that is indeed what's happening on the Earth. So since the Industrial Revolution, we have emitted 2.3 teratons of carbon dioxide, okay? It's kind of a large number. 2/3 of that, I want to emphasize, has been emitted since I was born. And I'm old, but I'm not that old. I was born in 1977, and almost all of this transformation of the atmosphere, the large majority of it, has happened since I was born, right? And I'm kind of middle-aged. So we really we are changing fundamentally the atmosphere of the planet in a human lifetime, right? So this is absolutely not sustainable in any way. And of course, the increase in the greenhouse gases has a measurable effect on the temperature, as predicted. I mean, as predicted 140 years ago, but as predicted accurately 35 years ago now. If you look at the entire planet, we have warmed about 1 degree Celsius from 100 years ago, a bit more. And it doesn't sound like much, but first of all, that's in Celsius. So, you know, multiply by almost 2 to get to Fahrenheit. And another thing to keep in mind is that the warming is not uniform over the Earth. The land is warming much, much faster than the ocean. And so if you actually look at the average temperatures over land, we have warmed 3.5 degrees over the last century. 3.5 degrees Fahrenheit. Sorry, I'm jumping back and forth between the two. And so that's a pretty remarkable change. And even worse than this is the Arctic. The Arctic is warming even faster and is warmed about 5 to 6 degrees Fahrenheit relative to the rest of the planet. Sorry, it is warmed 5 to 6 degrees Fahrenheit, period, but much, much faster than the rest of the planet. And that has really important implications. By the way, these are just thermometer readings. This is out of Berkeley Earth. They didn't want to use other temperature tracers like, you know, tree ring thickness or anything like this. They just wanted to use thermometers. Because they were such skeptics to climate science conclusions, they were actually funded by the Koch Foundation, you know, fossil fuels, and they came to the exact same conclusion as climate science had before, but the physicists had to do it themselves. But let it be shown that the climate scientists before them were actually doing it all right and getting the right answer before. So yeah, the greenhouse gases are the key here. We put a bunch of extra greenhouse gases in here. And what this effectively has done is changed the effective amount of, they call it solar forcing, amount of radiation that we're feeling on the Earth's surface by about 2 watts per square meter, right? So this is about 1%. But by century's end, this number could get much larger. If we changed everything dramatically today and started rapidly decreasing our carbon dioxide emissions, it might be 2.5. But if we kind of do business as usual and keep digging up the rest of the fossil fuels, it could be 7 watts per square meter. And what that means in terms of temperature is right now we're at about 1 degree Celsius, but it could be as high as 1.6 in kind of a best case scenario. to as high as 3.5 degrees. 3.5 degrees Celsius. Okay, so right now we're at about 1 degree. 3.5 degrees is very scary. So these the effects of this temperature rise are happening now, and these are sort of obvious first-order effects that you would predict, right? As ice melts on land, it goes into the ocean, and we get sea level rise. As the surface of the ocean is warming, the hurricane intensity increases because it gets its energy from thermally from the ocean. Routes are increasing for two reasons. One of them is that, of course, when it's warmer, it dries out the land faster. It's a very direct, straightforward effect. And the really big one is that the Arctic ice is melting very quickly in these warmer temperatures. I want to just point this out. This is the volume of the Arctic ice cap throughout the year. Obviously goes up and down. Every year since the year I was born. That's the year they launched the satellite. And in the 80s, it was pretty stable, but then it started to collapse. And you don't have to squint. You don't have to do some fancy fitting. It's very obvious what is going on. Sorry, they're color-coded. The dark blue is 80s, light blue is 90s, whites are 2000s, and the reddish is 2010s. And the yellow line is this year. There's a rapid decline in the volume of ice over my lifetime. And it's especially problematic in the summer because as you can see there, about 2/3 of the volume has disappeared in my lifetime, right? Again, we are changing what the Earth looks like in a human lifetime. And that's particularly problematic because the Arctic sea ice in the summer reflects a lot of sunlight. And now the ocean that is now there is now absorbing most of that sunlight. And so we're changing sort of the equilibrium temperature of the planet that way. But what really scares me are not the sort of physics things, right? What equilibrium temperatures are or ice melting. It's not the physics, it's the biology or the the atmospheric sciences that really scares me. So what I'm very nervous about is, ecosystem collapse. And the reason I'm nervous about this is all of these ecosystems have been in a fairly stable equilibrium for 10,000 years with constant temperatures. And when we take them out of that equilibrium, there are going to be winners and losers. And I don't think we're ready for this. And one example that I like to give for people in the American West is the bark beetle killing billions of trees. This is a beetle that has been around in these same ecosystems. It's not invasive for millennia, but the warmer winters and the prevalence of droughts has allowed them to proliferate. And they've done far more damage to our forests than environmentalists were trying to prevent, with deforestation, with chainsaws and whatnot. So this is an ecosystem that is out of equilibrium and really changing what the American West looks like. It's the same with the coral reefs. The coral reefs are very sensitive to temperature differences. And also the shallow ocean is acidifying because it's absorbing carbon dioxide, which creates carbonic acid in the water. And it's killing all of the coral reefs worldwide. And these are really, really important ecosystems for the shallow tropics because the water is not nutrient rich in the tropics. And so the marine life in the shallow tropics really is centered around these locations. So this is a very big deal. And then finally, another really scary thing is the changes in atmospheric currents. The jet streams, the polar vortex, these things you've heard of, they are dictated, the strength of them is caused by temperature differences between mid-latitude and the Arctic, between different latitudes. Combined with the Coriolis force. And the Arctic has warmed much, much warmer than mid-latitudes. And because of it, the strength of the jet streams have decreased and have become unstable. And you've heard of this, when the polar vortex, when they become unstable and this Arctic air, which is normally contained up here, is allowed to come down in the winters, for example. So, this is what dictates when and where weather systems arrive on our planet. And we're actually changing the latitude of the jet stream and its strength and stability. So this is what scares me and why we need to move. So what do we do about this? Well, the Intergovernmental Panel on Climate Change, the IPCC, 2 years ago said, you know what, we need to very seriously, everybody had been talking about keeping warming to 2 degrees. But they kind of sounded the alarm that we should probably be considering trying to keep the warming below 1.5 degrees Celsius. And they came out with this report and showed what we had to do. And it's not simple. Well, I'll back up a little bit. These are 4 scenarios here. But basically, this is how many tons of CO2, billions of tons, gigatons of CO2 we are emitting into the atmosphere every year, and what we need to do in the future to arrive at no more warming than 1.5 degrees Celsius. And we can just reduce our emissions to 0 very quickly, or we can sort of delay it a little bit, but then we need to somehow capture tens of gigatons of carbon dioxide and sequester it underground towards the second half of the century. And we don't really know how to do that yet. But regardless, what this basically means in the near term is that we need to decrease our carbon dioxide emissions roughly by half by 2030. And on the latter half of the century, sequester carbon dioxide on massive scales, tens of gigatons of carbon dioxide per year. This is probably not going to happen, right? Our planet runs on fossil fuels, and undoing it by 50% in 10 years is extraordinarily challenging, right? But a 2-degree scenario, which is plausible, still requires a reduction of 50% in our carbon dioxide emissions. Maybe not by 2030, but by 2040, 2045 maybe, depending on a few things. That is still very fast. And there's nothing magical about 1.5 or 1.6 or 1.7. Every 1/10 of a degree makes it worse. And so my thought is we should be shooting for 1.5 and definitely not get over 2. So one of the big conclusions when you see this report is that we need fundamental transformation in where we get our energy, not just efficiency, right? So this is what has changed my thinking from 15 years ago when I wanted to get my LED light bulbs, or I wanted to drive a more fuel efficient internal combustion engine car. We can't efficiency our way to 0. Most of our energy uses have fundamental limits on their efficiency, of course. The energy is the point, and therefore we can't get to 0 if we continue to use those the same fossil fuels for that energy. For example, you can't drive a 2-person wide vehicle at highway speeds at better than 70 miles per gallon. You can't do it. There are kind of thermodynamic limits in our engines, and the drag force is fundamentally constraining us. You can't get more light out of an LED bulb for less energy anymore. We're almost there, essentially, with perfect efficiency. Light is energy, and that's the point of it. That's it, right? So we need new energy, right? We need a transformation in where that energy comes from, and it can't be a carbon emitting or a greenhouse gas emitting source. And one thing I want to emphasize is, we say we have 10 years or maybe 15 years or whatnot to reduce our emissions by half. But what this means is we have 0 years to start. And that's the critical thing. A lot of the things we need to change in our society have lifetimes of 10 to 15 years, right? Our vehicles that we're driving around, our single most important greenhouse gas contributor in California and in the country, they last 10 to 15 years. Our appliances, hopefully, last 10 to 15 years. Air conditioning, those last 15 years, right? So if we start today, and when these things need to be replaced, we replace them in the natural replacement cycle. We replace them with something that doesn't contribute to climate change, then we can get there, right? So that's the idea behind this. And delaying this further, right? If you need to buy a new car this year or next year, and you continue to buy one that contributes to this, you've just delayed action for another 10 or 15 years. So, all right, now let's talk about energy. I love this diagram. I teach a large class on energy and the environment, and we basically dissect every part of this, this diagram. This is energy consumption in the United States. On the left-hand side is the source of the energy, from solar to petroleum at the bottom here. And where it goes was used for, a lot of it's for electricity generation, residential, commercial, industrial, and transportation. And the units here are in quads, which is a really weird unit. It's a quadrillion BTUs, which, I'll just translate it for you. It's 10 to the 20 joules, okay? And that's just one thing to emphasize. We are an enormously energy intensive society, right? This is a gigajoule per person per day in the United States, right? This is crazy. This is taking a small car, like a ton, and lifting it into low Earth orbit, 100 kilometers into the air. That's a gigajoule. I know gravitational force is not that strong, but it's still a lot of energy, okay? So, and the other thing I'd like you to notice is that this number is 100, and it's actually been 100 for several years now. And it's kind of nice because what this means is all these numbers here can be thought of as percentages. This is 1 out of 100. This is 36 out of 100. So these are basically effectively percentages, and it makes it very easy to analyze. So one thing that I'd like to point out is that 2/3 of all of the energy consumed on the left over here ends up in this box here as rejected energy. This is totally wasted energy that doesn't do anything for us in the end, right? It doesn't provide a service for us. It's just wasted in the process. 2/3, right? So it seems like a good chunk to deal with first, right? And where are those coming from, right? That's, oh, sorry, these pipes are showing you, where one thing is going from the other. And the width of the pipes or whatever, ribbons or whatever, is how much energy there is. But the largest chunk, 24% of all of our energy is coming from wasted heat, wasted energy from electricity generation. And the other part is transportation, almost as big, huge amount of wastes. And that's the large majority of all of the wasted energy, okay? So why are we wasting all this energy? Where is this going? So now we're into the physics. In both cases, the reason this energy is wasted is because we are using heat engines, and we're not interested in heat, where we're interested in mechanical work, right? So heat engine is something that converts thermal energy into mechanical work. And typically the efficiencies are pretty low and have to be fairly low due to the second law of thermodynamics. And the hotter you can burn the fuel, the better, of course. And you can look at like the ideal engine that can do this, the Carnot engine. And the efficiency, which is just defined as the amount of work you get out compared to how much thermal energy you put in. Ideally, you'd like it to be close to 1, but it's 1 minus the cold temperature or the ambient temperature that you're burning this thing in and it's doing work against, compared to the hot temperature of the hot gas that's, like steam or the exhaust from the combustion. So, I mean, this is the ideal efficiency, and we're not even remotely close for a whole bunch of reasons to ideal Carnot efficiencies. And so transportation, most of our emissions and most of our energy is used in internal combustion engines, like on the right here, a 4-stroke engine. And in gasoline engines, our efficiency is about 20%. 20%. 4/5 of that energy is lost in the form of heat out the exhaust pipe or just heating the engine block, okay? Now diesel engines, because we burn that diesel at higher temperatures and pressures, we can get up to 30% or so. But again, the vast majority of that energy is wasted. So that's the temperature portion of that lost wasted energy, but it's also wasted in power generation, electric power. And these are turbines, right? So this is a steam turbine on the right, where you might produce steam in a coal plant and turn these turbines to produce electricity in a generator. But again, a coal power plant is typically about 30% efficient, so it's wasting the vast majority of the energy. And natural gas power plants are more efficient. We burn that gas at much higher temperature, but it's about 50 to 60% efficient. So again, we're wasting about half of the energy. And I want to emphasize, all of this is coming from heat when it's not heat we want, right? And so there's a lot of wasted energy there, but where's that energy coming from for most of this stuff? Well, for electricity generation, the vast majority of this is coming from natural gas and coal. And for transportation, it's coming from petroleum, gasoline, right? So it's actually fossil fuels that are providing this energy, and those fossil fuels are emitting carbon dioxide. So this is a great figure here, but it's breaking things down in terms of energy. But we also want to look at this in terms of greenhouse gases, right? And so I will kind of, I did some calculations and I switched this around here, okay? So here's our greenhouse gas emissions pie chart. And I've broken these down so that, the two biggest sectors here are transportation, where we have all of that wasted heat in heat engines, and electricity, where we, again, have tons of wasted heat. And it's also the two biggest pieces of our carbon dioxide pie in our country. So that seems like a very obvious place to tackle these things. So obviously, we don't want heat engines. We never wanted heat in the first place. It was just an indirect way to get to work or electricity production. What are some alternatives to heat engines? So for electricity production, you kind of know the usual suspects. Obviously, solar power, photovoltaic solar, where you do not need to make a heat engine at all. It's just directly converting the sunlight's energy into electric energy. Wind power, where you've taken out the middleman of the steam turbine, and you just have a wind turbine producing electricity. Hydropower, you can produce electricity in fuel cells. None of this requires heat engines, okay? I will make a caveat here that I will allow some heat engines, okay? Nuclear is, we use nuclear essentially as it's a heat engine. We create steam and produce electricity with, it's a heat engine. And geothermal is the same, but these are carbon free. And frankly, I don't want to depend on these. I'm nuclear agnostic. We should definitely keep our existing nuclear fleet going. But I don't think it's going to save the world in the time we need to save it, especially next generation nuclear. But anyway, so that's why I'm focused on the other things in the first bullet point up here. And, you know, this is real. We are doing this now in California. We're like at the tip of the spear on decarbonization in the country. And last year, 58% of our electricity was carbon free, and it's been rising every year. I suspect we'll be over 60% this year. Actually, it might be significantly higher because of COVID. And then alternatives to heat engines on the transportation side, you know where I'm going with this. Once all of this electricity is clean, when we produce it with these wind and solar and whatnot, you can use that clean electricity in electric motors to make electric vehicles. And these motors are extremely efficient. And unlike internal combustion engines, greater than 90% of the energy in your battery is converted to actually mechanical energy in the car, okay? And they're just wildly simpler. I could give a whole talk on this. You know, the typical electric vehicle today has 20 moving parts, and they're kind of mostly the parts you want to move, like the axle. But the typical internal combustion engine has hundreds or thousands of pieces. It's hard to convey, right? But there's no like exhaust system. There's no valves. Because there's no valves, there's no timing belt, there's no oil, there's nothing to clean the oil filter. There's no radiator. There's no transmission. There's one gear. It's wildly simpler. It's cleaner. There's no exhaust or carbon dioxide if you use clean electricity. It's quieter. It's got better torque, way lower maintenance because of the fewer moving parts. And it's about 30% cost per mile when you drive. Of course, I'm ignoring this very expensive battery that you have to buy, but nonetheless, we're getting there. And there's reasonable alternatives to existing cars, right? So this is the Hyundai Kona Electric. This is a reasonable replacement for a lot of standard cars, and it's the car I own. Down here, I put the Ford Rivian. Well, sorry, the Rivian truck, which is backed by Ford. This is a truck that's coming out either later this year or next year. I recognize that the 3 best-selling cars on the road in the country are trucks. And then shipping, at least short-haul shipping, I think is really interesting for electrification as well. So how are we doing? How clean is our electricity? You can actually, you know, our grid is really weird and split up in this country. We should fix that. But you can look at the typical emissions factors, how much carbon dioxide is being emitted for every unit of energy, every megawatt hour of energy all over the country. There's some really bad areas, like right in the heart of the country, because they're almost purely reliant on coal. And there's some really good places like in California, right? So California, the grid that we are on, which services SoCal, Edison, PG&E, and SDG&E, it's pretty clean. We're getting down to 470 pounds of carbon dioxide per megawatt hour, which is much, much better than the rest of the country. However, you guys at Occidental are not powered by SoCal Edison. You have LA Department of Water and Power electricity, I believe, and your emissions are much, much higher. 750 pounds of carbon dioxide per megawatt hour. This is actually very similar to what's happening in the city of Riverside, where I live. And it's fascinating. I think LA Department of Water and Power is kind of a perfect example of the difficulties of transitioning to clean electricity. So what's the breakdown of your sources of power? Well, about a third by law has to be, by 2020, has to be renewable. So, and it is. But the big problem for LA DWP is this chunk right here, coal. We don't have any coal power plants in California, but LA DWP has coal plants outside of California that they bring in via high voltage transmission lines. And 18% of your electricity is still from very, very dirty coal. And it's actually coming from this plant here. This is the Intermountain Power Plant in Delta, Utah. It's still running, and it's going to run for another 5 years, 5 or 6 years. So this is kind of emblematic of the problem that we're dealing with in the country, that we have these assets that have multi-decade lifetimes, and we need to change things on a single decade timescale. And because of it, these are stranded. These are going to be stranded assets. We have to throw them away, junk them, even though they have, could be used for longer. LADWP already did this for the Navajo generating station in in 2017. They got out of it early, which is great, but they still have this other one, Intermountain Power, a coal plant. And the interesting thing here, at the location of this plant, they want to build a natural gas plant in 5 years, 6 years, to start with a new natural gas power plant, a new carbon emitting plant starting in 6 years. It's fascinating. But the reason is because they need that minimum amount of 800 megawatts in order to transmit all of the clean energy, wind and solar, they want to transmit across that high voltage transmission line from Utah. And they're also going to make this gas plants such that it can actually take hydrogen instead of natural gas in the future, when we think we can create hydrogen from clean electricity. So it's a very interesting time. They also have these 3 really dirty natural gas power plants, older power plants that they were supposed to redo so they were cleaner. This is in El Segundo, Long Beach, and Seal Beach. And they said, we're getting rid of those. And then actually a few weeks ago, they were like, okay, just kidding. We're going to still use them occasionally for when we have these massive power demands because of climate change is warming our summers. So it's an actually really interesting time when they're supposed to be getting rid of these plants, and they're still heavily reliant on natural gas. Okay, so that's all great. And we addressed a huge chunk of the puzzle there, but there's pretty large chunks of fossil fuels, primarily in the form of natural gas, a little bit of oil and biomass, but mostly natural gas, coming into our homes, and then also coming into our buildings and our stores and whatnot. Almost all of this is for heating. So I just spent this whole time saying that we were using heat engines when we didn't want heat, and so it was very wasteful. Now I'm going to say that we're using this for heat. We're burning things for the heat, and it's much more direct and more efficient. And I'm going to say that we shouldn't do that either. So what am I talking about? By the way, that chunk of heating this is heating our homes, heating our water. It's about 10% of our carbon dioxide emissions nationally, and actually in the state as well. So it's, we already dealt with this one. I mean, we have a path for dealing with this. We have a path for dealing with this. This is a nice big chunk of the puzzle next. So what are the alternatives to these natural gas furnaces that are warming our space and the water heaters that are warming our water? The better solution is a reverse heat engine, right? I was saying heat engines are very inefficient and we shouldn't use them, but reverse heat engines are nice, right? We refer to these as heat pumps. And what they're doing is using mechanical energy, typically in our case driven by electrical energy, to move heat from one location to another. You guys all have a couple of these in your houses. Air conditioner is a heat engine, and a refrigerator is a heat engine, right? It's using electricity and a compressor, the mechanical energy, to move heat out of your home or out of your refrigerator. We can actually reverse the flow of the refrigerants in these air conditioners, and they can actually heat our home in the winter. And we can also put these heat pumps on our water heaters too, to heat our water. And these heat pumps are really, really efficient, right? Typically, they provide about 4 times the thermal energy, 4 times more thermal energy than the electrical energy required to run them, okay? So that's, instead of losing energy, we're like almost magically, it's not magical, it's, you know, much more ordered, lower entropy energy, but we're creating we're moving extra energy and getting about 4 times more of it where we want it than the electrical energy consumed. And of course, that electricity can be clean as well, right? As our grid gets cleaner. So let me just remind you of what an air conditioner does. You know, typically your home is sitting here with the cold coils here inside your home. You blow warm air from your home over it, and that warm air deposits energy into the coil, and the air cools down, right? And the refrigerant here moves along, gets compressed into a hot temperature, and then you blow outdoor air over it to take energy away, and then you let the refrigerant expand and cool, and then you blow warm air over it and put energy back in, and do this in a loop, okay? That's what's happening in your air conditioner. But all we have to do is move the house to the other side, and it works perfectly well, right? It's the exact same principle. It's just that now the hot coil is inside the home. And of course, you don't actually have to move your house or undo all this stuff every winter and summer. You can just put a reversing valve here and reverse the flow, and this will be hot when you want to heat and cold when you want to cool, okay? It's really all it is an extra reversing valve on the same types of systems we have in our homes now. So heat pumps really should be used for all warming. And I use the word warm and not heat because there is a word of caution here. The efficiency of the heat pump goes down at the higher temperature you want, right? So this is not good for really high temperature applications like industrial applications, making steel or anything like that. But it's very efficient for making 80-degree air in your home. So space heating. All you have to do is when you change your central air conditioner, replace it with an air conditioner that has a reversing valve, a heat pump. That's what I did in my home. There's even crazier things going on. There are 28 million homes in the country that use electrical resistance, running electricity through wires for resistant heating. Most of those are in the South. The South, their electricity grid actually peaks in its demand in the winter. You would think it would be air conditioning. It's actually in the winter because they use resistance for heating in the winter. That should be immediately addressed. All of these places have air conditioners. It's hot and humid down there. When they replace them, they should simply put this reversing valve in. Okay. And water heating, same thing. 110 million household water heaters throughout the country. Almost none of them are heat pumps. About half of them are gas, and about half of them are electrical resistance, which again is very, very inefficient. You're using a high quality form of electricity to make heat. It's really dumb. And the cool thing about heat pump water heaters is that it's very valuable for energy storage. One big problem with all of these renewable sources of electricity, like in California, is our electricity grid is very cheap and clean. Our electricity is very cheap and clean in the middle of the day because we have a lot of solar power. But at night, we still have to run these gas plants. And if you have a heat pump water heater, you can actually use clean electricity efficiently with a heat pump in the middle of the day and store it so that you can use that hot water throughout the night. California is really getting on board with this, and I think in like a year or two, every new heat pump, every new water heater in the state is going to be heat pump. I mean, they're throwing money at this. Like Sacramento's utility is actually just paying for everything if you get a heat pump water heater. Installation, they heat pump everything. So putting it all together, sorry, I don't have the time. Oh wait, I can find out. Okay, I gotta hurry. All right. So putting it all together, removing heat engines is a 56% reduction in carbon dioxide emissions. Installing reverse heat engines gets you another 10% reduction in carbon dioxide emissions, right? So together, these two things reduce your carbon dioxide emissions by 2/3 with existing technology and replacement of things in their natural replacement cycle over the next 10 to 15 years, right? So all of this was a lot of stuff, but I made a meme to make this much simpler. Heat engines are bad and reverse heat engines are good, right? And really, this is the key to 2/3 of our carbon reduction. And I'll just point out that this other big piece of the puzzle that's here in red is industrial heat, high temperature heat, which you don't want to use, you can't really use heat pumps for, and you don't really want to use electrical resistance for. This is steel production, cement production, and it's a huge piece of the puzzle. But if you have a whole bunch of abundant, clean electricity, you can actually use that electricity to create hydrogen through electrolysis. And if you store it where we currently store our natural gas, you can provide hydrogen to burn for high temperature applications. So this pathway of electrification provides clean sources of high temperature heat that can address this other huge piece of the wedge as well. And California a little bit, but Europe is really investing heavily in this. So just to reorganize for non-physicists, all this means is that we need to clean and expand our electric grid, right? And we need, once we have that, well, as we are cleaning and expanding the electric grid, we need to electrify everything. We need to electrify our transportation, and we need to electrify our space and water heating. I am not the first person to come up with this. There are huge groups doing this now. And I recommend this thing that came out, this report that came out about a month ago called Rewiring America, that is specific to our COVID era, saying that, listen, we need a World War II effort while people need jobs to electrify everything and reduce our carbon emissions by half in the next decade. And it's kind of a pathway forward. This is by a physicist, by the way, MacArthur Award winner. I have a lot more to say, but I'm going to stop here. Thanks. I see Professor Stierwalt is standing up, so.
Thank you, Brian.